Okay, so the last section in chapter 1 is 1.6, where we're going to look at instantaneous rate of change. So if we flash back and recall from our last class, which was on Friday, we looked at average rate of change. And using a quadratic as an example, we determined or remember that a secant line touches our graph in 2 spots. Okay, so if we have a point A and B, our secant line here would represent the average rate of change, which is the exact same thing as the slope, which we did in grade 9 and grade 10. So we can say that our average rate of change is our slope between A and B, and that represents a secant line. Okay, and at the end of class on Friday, we were looking at looking at the distance between the x values. And so we'd have, like, this point was labeled x1, y1, and this point was labeled x2, y2. So we could take those 2 points and turn them into function notation. And we have x2, f of x2, and x1, f of x1. And then we started talking about, all right, well, we're looking at finding the average rate of change tells us what's happening over like a certain period, but the instantaneous rate of change is, well, what's happening at that exact instant. So what would be happening there is we're going to take this second point and move it very close to our first point. So it's going to be sliding down. And what's going to happen as it gets very close, the difference between the x values becomes very, very small. Okay, so we started looking at, well, if we can define x2 as saying, well, that's x1 plus a little bit. Okay, and similarly then, y2, which was f of x2, would now be f of x1 plus h, where h is just that little tiny bit. And what we're going to look at happening, or what we're going to try and find out is, well, what happens when h gets very close to 0? Okay, when h gets very, very close to 0, and by this we're saying, all right, well, let's see when h is 0.001. Okay, what's going to happen is when h gets really, really small, is that we can take the second point, and as h gets really, really small, it's going to be getting very close to that first point. Okay, and what happens when a graph goes from touching, a line goes from touching a graph at 2 points to touching it at 1? What do we call that? That's a tangent line. And what does a tangent line represent? Instantaneous rate of change. So when h gets really small, it's going to become a tangent line. And this average rate of change becomes an instantaneous rate of change. Okay, and the slope between A and B, those 2 points, that's going to get very close to the slope just at A. Okay, so we're going to get rid of the second point. It's going to get almost go away. And so we're going to get the slope, the average rate of change is going to get really, really close to the instantaneous rate of change. So you will see questions in your textbook and on assignments and on your test in a couple days. And the questions will be worded as follows. It'll say calculate the instantaneous rate of change of the function Okay, so calculate the instantaneous rate of change of the function negative 4.9 t squared plus 25t plus 2 when t equals 2. Okay. Okay, so if we recall from Friday and even earlier today, well, what's the equation for slope? Okay, so it's y2 minus y1 over x2 minus x1, and we change that into, say, now we could change that y2 minus y1 over x2 minus x1, and we, over here, we're looking at changing things into function notation and putting everything in terms of x1. So we could write that as f of x1 plus h minus f of x1 over x1 plus h minus x1. So we did that on Friday. Okay, so looking at that question, what will be asked is, okay, how do I apply that to this question? Okay, and specifically, all right, well, why don't I just make h 0 and go from there, just get rid of it? Well, what will happen if you make h 0 is you're going to have x1 minus x1 in the denominator, which is going to give you a 0 in your denominator, which you can't divide by 0, so it'll make things blow up. So what we do is pick a number that's very, very close to 0, but not 0. Okay, so what we'll do for this question, we want to find out, we're looking at when t equals 2. Okay, so what we'll do is, okay, so what we'll do is we'll take 2, and then we got to take a number very, very close to 2. Okay, so like 2.1, 2.01, 2.001. What I'm going to say for our purposes, 2.1 is not close enough. Okay, so I want, say, at least 2 or 3 zeros. So how you could do that is we'll say for this question, our solution is going to look like, well, our instantaneous rate of change, I kind of get tired of writing instantaneous rate of change out. We can say we need to evaluate that function at 2.001 minus when we evaluate it at 2. And then we're going to have 2.001 minus 2. Okay. Well, the denominator, that's very easy to work out. We're going to be dividing something by 0.001. And now we got to work out, well, how do we got to work out the value for f of 2.001. And as well, the value for 2. So we take those two t values and plug them into our equation. Okay, so we can plug those in, and we're going to get for f of 2.001, 32.405395, and for f of 2, 32.4. I'll stress leave lots of decimal places in your answer. Reason being is that at the end we're going to be dividing by 0.001, so we need to be able to move our decimal place over 3 spots and still have accurate answers there. If we round too early, we're going to end up in trouble. Okay, so if we plug those back into our equation, we're going to get our instantaneous rate of change is going to be 32.405395 minus 32.4 over 0.001. So we perform that subtraction in the numerator, and what do we get? Okay, and then we divide it by 0.001, and we're going to get 5.5 Okay, 5.395. And then we're going to throw some units in there. We're talking about meters per second. Okay, so our instantaneous rate of change at 2 is approximately equal to 5.395. Why is it approximately equal to? We're rounding made up numbers, both of them. It's not exactly at 2 because we did an average rate of change between 2 and 2.001. We could have chose 2 and 2.0001. The smaller the number that is different, the more accurate your answer is going to be. But you get a fairly accurate answer if you go 0.001 above or below. So that'll be good enough for kind of what our needs are.